Have you ever wondered how a tiny electronic component can control a powerful motor, an LED, a relay, or even hundreds of watts of electrical power? That component is the MOSFET. In this video, I'll explain exactly how MOSFETs work, their terminals, types, operating regions, applications, and even how to build a simple MOSFET circuit. MOSFET stands for Metal-Oxide-Semiconductor Field Effect Transistor. It is a voltage-controlled semiconductor device. Unlike current-controlled transistors, a MOSFET responds primarily to the voltage applied to its gate. You will find MOSFETs used for switching, amplification, power control, motor control, pulse width modulation or PWM, power supplies, and digital electronics. In modern designs, they are one of the most important devices for efficient power handling. A MOSFET has three primary terminals: the gate, the drain, and the source. The gate is the control terminal. The voltage between gate and source determines whether current can flow from drain to source. The drain is where the main current enters or leaves, depending on the configuration, and the source is the other end of the controlled path. Always remember that the physical pinout is not identical on every package. An IRFZ44N in a TO220 package has one arrangement, while a surface mount device may be completely different. Check the datasheet for the exact pin connections of the part you are using. To make the concept intuitive, think of a water pipe with a valve. The water flowing through the pipe represents electric current. The valve itself represents the conductive channel inside the MOSFET. The handle that opens or closes the valve is the gate voltage. When you turn the handle, you open the valve and water flows. When you close it, the flow stops. In the same way, the gate voltage opens or closes the channel between drain and source, controlling the current. This simple analogy helps many students grasp why a MOSFET is called a field effect device. An electric field from the gate controls the channel without significant steady-state current into the gate itself. MOSFETs shine as electronic switches and as dimmers. Consider a basic LED switching circuit. A microcontroller, digital or PWM pin, connects through a small resistor to the gate of an N-channel MOSFET. The drain connects to the LED and its current-limiting resistor, and the source connects to ground. When the microcontroller pin is low, the gate-to-source voltage is near zero, the MOSFET is off, and the LED is dark. When the pin goes high, the gate voltage rises above the threshold, the channel forms, and the LED turns on. For brightness control, we use PWM. A high-frequency square wave with varying duty cycle is applied to the gate. The MOSFET switches fully on and fully off many times per second. The average power delivered to the LED changes with the duty cycle, so the brightness appears to change smoothly while the MOSFET itself stays efficient. The same principle appears in many practical applications. You can drive a relay coil with a MOSFET so that a low-power signal controls a higher power circuit. You can switch a DC motor on and off, or control its speed with PWM. LEDs, solenoids, heaters, and power supply switching stages all commonly use MOSFETs. In each case, the key advantages are high input impedance, fast switching, and low on-state resistance when the device is fully enhanced. Even though a fully turned-on MOSFET can have a very low resistance, it still dissipates power. The power lost as heat is given by I squared R, where I is the drain current and R is the on resistance. Suppose the current is 5 amperes and the on resistance is 1/10 of an ohm. Then the power dissipation is 25 times 1/10 or 2.5 watts. That heat must be removed. A heat sink attached to the metal tab of a TO220 package increases the surface area and keeps the junction temperature within safe limits. If the power dissipation is too high or the cooling is inadequate, the MOSFET can overheat and fail. Always calculate the expected power loss and provide appropriate thermal management. How does a MOSFET compare with a bipolar junction transistor? A MOSFET is voltage controlled, a BJT is current controlled. In the steady state, the gate current of a MOSFET is only a tiny leakage current, whereas a BJT needs continuous base current to stay on. Because of the insulating oxide under the gate, MOSFETs have extremely high input impedance. BJTs have much lower input impedance. MOSFETs are outstanding for switching applications, especially power switching, because they can be driven with simple logic levels and dissipate little power when fully on or fully off. BJTs remain excellent for many amplification circuits and certain switching tasks. The statement, MOSFET is always better, is not correct. The best device depends on voltage, current, speed, available drive, and cost for the particular application. Now let's build a simple practical circuit. Take a breadboard, an N-channel power MOSFET such as the IRFZ44N, an LED, a 220 ohm resistor, a 9 or 12 volt supply, and jumper wires. First, examine the circuit diagram. The source of the MOSFET goes to ground. The drain connects through the LED and resistor to the positive supply. The gate receives a control signal. When the gate-to-source voltage exceeds the threshold, typically a few volts for a logic level device or more for a standard power MOSFET, the channel forms and the LED lights. Remove the gate voltage or pull it to ground and the LED turns off. Use close-up views of each connection so that every terminal is clearly visible. A critical practical detail is the floating gate. The gate of a MOSFET is essentially a small capacitor with extremely high impedance. If you leave the gate disconnected, any stray charge can accumulate and leave the MOSFET partially or fully on, or even oscillating. That unpredictable state is dangerous in real circuits. The solution is a pull-down resistor for an N-channel low-side switch. Connect a resistor, commonly 10 kiloohms, from the gate to the source or to ground. When the driving signal is absent, the resistor discharges the gate capacitance and holds the MOSFET safely off. When an Arduino or other microcontroller drives the MOSFET, 2 resistors are recommended. A series gate resistor between 100 and 330 ohms limits the instantaneous current that charges and discharges the gate capacitance. This reduces stress on the microcontroller pin and can dampen ringing that might otherwise produce electromagnetic interference. The second resistor is the pull-down already mentioned. The complete connection is microcontroller pin to series resistor to gate, and from gate a pull-down resistor to source. Together they give reliable, safe switching. Brightness control can also be done with a potentiometer. The wiper of a 10 kiloohm potentiometer can feed the gate through a series resistor. As you turn the potentiometer, the gate voltage changes and the LED brightness changes. However, a slowly varying analog voltage often holds the MOSFET in its linear region, where the voltage drop across the device is significant and power dissipation rises. The MOSFET can become quite hot. For efficient LED dimming, PWM is almost always the better choice. If you do experiment with a potentiometer, monitor the temperature carefully and keep the current modest. MOSFETs come in 2 fundamental modes, enhancement and depletion. An enhancement mode MOSFET is normally off. At 0 gate-to-source voltage, there is no conducting channel. You must raise the gate voltage above the threshold voltage to invert the surface and create the channel. Most power MOSFETs used in switching are enhancement mode devices. A depletion mode MOSFET is normally on. Even at 0 gate-to-source voltage, a channel already exists and current can flow. Applying a gate voltage of the proper polarity reduces the channel conductivity and can turn the device off. Depletion mode parts are less common in everyday power switching, but appear in certain analog and RF circuits. The other major classification is N-channel versus P-channel. In an N-channel MOSFET, the majority carriers in the channel are electrons. To turn an enhancement N-channel device on, you apply a positive gate-to-source voltage. These devices are typically used as low-side switches, with the source grounded and the load connected between the positive supply and the drain. A P-channel MOSFET uses holes as the majority carriers in the channel. To turn an enhancement P-channel device on, you need a negative gate-to-source voltage. That makes them convenient for high-side switching. The source connects to the positive rail, and the load sits between the drain and ground. Understanding the required polarity of VGS is essential for correct circuit design. Many beginners become confused about polarity because they think only in terms of voltages relative to ground. The important quantity is always the gate-to-source voltage, VGS. Consider a P-channel MOSFET whose source is tied to plus 12 volts. If the gate is driven to plus 5 volts, then VGS equals 5 minus 12, which is minus 7 volts. That negative voltage is exactly what is needed to turn the P-channel device on. Always calculate VGS with respect to the source terminal of that particular transistor. not with respect to circuit ground. To understand what happens inside the device, we need a brief look at semiconductor physics. Silicon in its pure form is a semiconductor with 4 valence electrons. When we introduce impurity atoms with 5 valence electrons, such as phosphorus, we create N-type silicon that has extra free electrons. When we introduce atoms with 3 valence electrons, such as boron, we create P-type silicon that has mobile holes. The interface between a P-type region and an N-type region forms a P-N junction. The electric field and the depletion region at that junction give the diode its one-way conduction characteristic and are fundamental to the operation of the MOSFET. Look inside an N-channel enhancement mode MOSFET. The starting material is a P-type substrate. 2 heavily doped N+ regions are diffused or implanted to form the source and the drain. A thin layer of silicon dioxide, an excellent insulator, is grown over the surface between source and drain. On top of the oxide, a conductive gate electrode is deposited. When the gate is at the same potential as the source, the region under the gate remains P-type and no continuous N-channel exists. The device is off. As the gate voltage is raised, an electric field attracts electrons toward the surface. When the gate-to-source voltage exceeds the threshold, the surface inverts and a thin N-type channel forms, linking source to drain. Current can now flow. The higher the gate voltage above threshold, the more electrons are attracted and the lower the channel resistance becomes. The relationship between drain current and the 2 voltages, VGS and VDS, defines 3 operating regions. In the cutoff region, VGS is less than or equal to the threshold voltage. No inversion channel exists, and the drain current is essentially 0. The MOSFET is off. In the ohmic or linear region, VGS is above threshold and VDS is relatively small. The channel acts like a resistor whose value is controlled by VGS. Drain current rises approximately linearly with VDS. This is the region we use when we want the MOSFET fully on as a low-resistance switch. In the saturation or active region, VDS is large enough that the channel is pinched off at the drain end. Further increases in VDS produce little additional drain current. ID becomes nearly constant for a fixed VGS. Note carefully that the word saturation for a MOSFET does not mean the same thing as saturation for a bipolar transistor. In switching applications, we normally avoid the saturation region of the MOSFET and instead drive the device deeply into the ohmic region so that voltage drop and power loss stay low. An N-channel depletion mode MOSFET already has a built-in channel at VGS equal to 0, so it conducts. Applying a negative gate-to-source voltage repels electrons from the channel, narrowing it and reducing the current. With a sufficiently negative voltage, the channel can be completely depleted and the device turns off. A P-channel enhancement mode MOSFET is the complementary structure. At VGS equal to 0, there is no conducting channel and the device is off. Applying a negative gate-to-source voltage attracts holes to the surface, forming a P-type channel that allows current to flow from source to drain. Finally, a P-channel depletion mode MOSFET conducts at 0 VGS because a channel is already present. The proper gate voltage reduces the density of carriers in that channel and therefore reduces the current. In summary, a MOSFET is a voltage-controlled device with 3 terminals: gate, drain, and source. The 4 main types are N-channel enhancement, N-channel depletion, P-channel enhancement, and P-channel depletion. They are used for switching, power control, PWM, motor drives, and many other applications. Once you understand the meaning of VGS, the formation of the channel, the 3 operating regions, and the practical details of gate drive and heat management, you have the foundation needed to design and troubleshoot real MOSFET circuits. If you found this explanation useful, subscribe for more practical electrical and electronics tutorials. Turn on the notification bell, and I'll see you in the next lesson.